All right, guys, I'm going to uh, work through the second example in this section. This section is application of the second derivatives, and we try to use the second derivative test to locate the extrema of a function f. We did one example in the previous section to find the extrema of a function by using the first derivative test. Now we're going to show another example and using a different approach. That's called the second derivative test. So we're going to use second derivative to locate the extrema of the function. There are some common steps for these two different approaches. The first step is always to find the critical numbers of the function. Okay. So in this example, the function f is 2x cubed plus 3x squared minus 12x minus 4. And then let's just find the relative extrema of f using second derivative test. Okay. So the first step is to find critical numbers of the function f. All right. Oh, wait. It's not t, it's f. It's me. So we already know how to do that. You just take the derivative of the function first and then set it equal to 0. Okay. Once again, this polynomial, so we don't have any numbers of x where the derivative does not exist. So the number of x, all the numbers for x prime to be 0, then include all the critical numbers. So let's just take the derivative. We know the critical numbers are defined as the number of x, so the values of x where the derivative equals 0 or does not exist. So we need to take the derivative anywhere. So the function is 2x cubed plus 3x squared minus 12x minus 4. So we just take the derivative term by term. So in the first term, the derivative of x cubed is 3x squared using the power rule. Multiply 3 by 2, so we get 6. And load the exponent by 1, so that gives us x squared. Okay. So that's the first term. Then we got 3x squared. So okay, let me just do this step by step in case people are not following me. All right, so that's first the term. Then we got second term, 3 times derivative of x squared. The derivative of x squared is just 2x as you multiply by 2 in the front and lower 2 by 1 in the exponent. So that's 2 minus 1. We get 1. So that's x to 1 or x. So we get 2x. That's derivative of x squared. And then minus 12 times derivative of x. The derivative of x is just 1. Now, the last term, the derivative of constant 4 is just 0. Okay, so that's the derivative, or the first derivative. So 2 times 3 is 6. So 6 times x squared, that's the first term. And then the second term is 3 times 2x. So that's 6x. And the third term is 12 times, so that's negative 12. And 0, we don't have to worry about it. So I'm going to factor out the f prime. So let's just factor out the 6 first, just like we did before in the example in the previous section. So if you factor out 6 from the terms, we got x squared for the first term, and we got minus x in the second term, and then minus 2 in the third term, right? Then we can further factor out, x squared minus x minus 2 as 6 times x plus 1 minus 2, isn't it? So once again, what they do is just find two numbers so that the multiply is two numbers, so you get -2. So 1 times -2, you get -2. And if we add two numbers, so you get -1, the coefficient of x. So 1 plus -2 is just -1. So that's right. So then we can find the critical numbers by setting f prime equal to 0. Okay. So then we can easily solve the equation to get the two critical numbers, and these critical numbers are, if you set x plus equal to 0, x plus 1 equal to 0, you're going to get -1, right? And also if you set x minus 2 equal to 0, you're going to get the x equal to 2. Okay, so let's just solve these critical numbers. So we got two solutions: x equal to -1 or x equal to 2, right? So this two critical numbers. Okay, so now we're going to use the second derivative test. We don't use the subintervals. Remember in the first derivative test, we use the critical numbers to split or divide the whole domain of the function into several subintervals, and then we pick up a test number in each subinterval and see the sign of the derivative of the function, and then determine whether it's increasing or decreasing. And then we draw the diagram, and we can determine the extrema, whether it's maximum or minimum. But in the second derivative test, we don't have to do all these steps. Instead, we're going to use the second derivative of the function. So in order to do that, then we need to take the second derivative of the function. Let's just do that. Okay, so the second derivative function is just the derivative of the first derivative. And we know the first derivative is 6x squared minus 6x minus 12. So if you take the derivative of f prime, you're going to get 6 times the derivative of x squared. As we know, that's just 2x. We already did that so many times, so I'm not going to repeat that. And the second term, -6x. If we take the derivative of x, we get 1. So that's -6 times 1. Okay. And in the third term, the derivative of 12 is 0, so subtract 0. So then if you simplify the result, you get the 12x. So 6 times 2 is 12. And then -6 6 times 1 is 6. Okay, so then we just plug in each critical number and find out the sign of the second derivative. So let's just do that. So at x equal to -1. So we just plug in -1 for x and find the sign of the second derivative. So that's 12 times x, 12 times -1 minus 6. So what do you get? So 12 times -1 is -12, and if you subtract 6, you get -18. Okay, so that's less than 0. So according to the rules, the second derivative of the function at the critical number is negative, then the function f attains a maximum. Okay, so thus the function f a maximum, a relative maximum or local maximum. Okay, so that's the first critical number, and then we have another critical number, x equal to 2. So once again, we just plug in positive 2 for x in f prime, f double prime. So this time what we get is so f double prime 2 will be 12 times 2. Okay, minus 6 if we plug in 2 for x. So 12 times 2 is 24. 24 minus 6, so that'll be positive 18, isn't it? So that's positive. So once again, by the rules of the second derivative test, if the second derivative of the function at the critical number is positive, then the function attains a relative minimum. Okay. Thus, if a relative minimum. So that's the second derivative test. All right.